we've seen how to represent lines and planes that contain the origin. How do we represent those that don't contain the origin? So let's say we want to represent a line that does not necessarily contain the origin. Well, we start with a line that does go through the origin. Now, we know that the points forming that line form a vector space, big V. We're going to translate that line by adding a vector c to every vector in big V. So here's the mathematical formulation of that. And we'll abbreviate that in this way, c plus big V. What we get is the line through the point C instead of through the origin. Let's try the same thing for a plane. How do we represent a plane that does not contain the origin? We start with a plane that does contain the origin. We know that the points of such a plane form a vector space, big V. We're going to translate this by adding a vector c to every vector in big V. Looks like this, and we abbreviate it c plus big V. And what we get is a plane that goes through C and not through the origin. Now, if C is a vector and big V is a vector space, C plus big V is called an affine space. So examples are a line or a plane that doesn't necessarily go through the origin. Let's do a more concrete example. Take the points u1, u2, and u3. We want to express the plane through these points as u1 plus big V, where big V is the span of two vectors. Okay. So big V looks like that. Well, we define big V as span of A and B, where A is the second vector minus the first, and B is the third vector minus the first. Now, let's look at u1 plus big V. It's the translation of a plane, so it too is a plane. Now, span AB contains the 0 vector, so u1 plus span AB contains u1. Span AB contains A, which is u2 minus u1, so u1 plus span AB contains u1 plus u2 minus u1, which is u2. And similarly, span AB contains B, which is u3 minus u1. So u1 plus the span of AB contains u1 plus u3 minus u1, which is u3. So u1 plus big V contains u1, u2, and u3. And it's a plane. There's only one plane containing those 3 points, so this is it. Now, we've written the plane containing these 3 points as this sum, u1 plus the span of u2 minus u1 and u3 minus u1. There's a nicer way to write this. Let's rewrite the u1 plus span of u2 minus u1, u3 minus u1. This is the set of all vectors u1 plus alpha u2 minus u1 plus beta times u3 minus u1, where alpha and beta range over all real numbers. We can use the distributive law and then gather like terms. Then it's the set of all linear combinations where the first coefficient is 1 minus alpha minus beta, where alpha and beta are the other 2 coefficients. So we'll do a substitution. We'll replace 1 minus alpha minus beta with another variable, gamma, and require that gamma plus alpha plus beta equals 1. So this is the same set. And this is a nicer representation of that set. So we call this linear combination, where the coefficients are required to sum to 1, an affine combination. More generally, if you have vectors u1 through un, a linear combination of those vectors is an affine combination if the coefficients sum to 1. And the set of all affine combinations of u1 through un is called the affine hull of those vectors. So using the same argument as before, we can see that the affine hull of u1, u2, and so on up to un can be written as u1 plus the span of all these vectors, u2 minus u1, u3 minus u1, and so on up to un minus u1. So this shows that the affine hull of vectors is an affine space. So we see that we can represent a plane as U1 plus a vector space, an affine space, or the affine hull of some points. There's a more familiar way as the solution set of an equation, ax plus by plus cz equals d. Let's rewrite this using vector notation. It's the set of all x, y, z such that the dot product of ABC with x, y, z equals d. In general, a point, a line, a plane can be written as the solution set of a system of linear equations. Remember, a linear equation is an equation involving the dot product with the vector variable. So here the linear equations are a1 dot x equals beta 1, and so on up to am dot x equals beta m. Well, what about the converse? Is the solution set of a linear system always an affine space? There's a simple counterexample. If you take a linear system that's contradictory, that has no solutions, for example, 1x equals 1, 2x equals 1, has no solutions. So the solution set in that case is empty. But we know that because a vector space always contains the zero vector, an affine space, which is u1 plus a vector space, always contains at least one vector, namely u1. So it seems like it breaks down. The solution set of a linear system is not always an affine space. But we've identified the one kind of counterexample, the one exception. And in fact, there's a theorem that the solution set of a linear system is either empty or an affine space. And we'll prove that. So here's the theorem we're trying to prove. We start with a concept. Each linear system corresponds to another linear system in which the right-hand sides, beta 1 through beta m, have all been replaced by zeros. And a linear equation, a dot x equals 0, with a 0 right-hand side, is called a homogeneous linear equation. And a system of homogeneous linear equations is called a homogeneous linear system. So what we've seen is from any linear system, we can derive the corresponding homogeneous linear system. Now, we already know that the solution set of a homogeneous linear system is a vector space. Now we use a lemma. Let u1 be any solution to some linear system. Then for any other vector, u2 is also a solution if and only if u2 minus u1 is a solution to the corresponding homogeneous linear system. Okay, remember, here's a linear system, and here's the corresponding homogeneous linear system. Now let's prove this lemma. Let u1 be a solution to a linear system, and for any other vector u2 is also a solution if and only if u2 minus u1 is a solution to the corresponding homogeneous linear system. So we start with u1. u1 is a solution, which means that it satisfies all these equations. That is, a1 dot u1 equals beta 1, and so on. Now, u2 satisfies the same equations if and only if the difference between a1 dot u2 and a1 dot u1 is 0, and so on up to am dot u2 minus am dot u1 is 0. All those differences have to be 0 because the right-hand sides have to match. And this is true if and only if a1 dot u2 minus u1 equals 0, and so on, using the distributive law. So we've shown that u2 satisfies those equations if and only if u2 minus u1 satisfies all these equations. That completes the proof. So here's the lemma. Let's see how we can use it to prove the theorem. We need to show that the solution set of a linear system is either empty or an affine space. Okay? Let big V be the set of solutions to the corresponding homogeneous linear system. Now, there are two possibilities. If the linear system has no solutions, then its solution set is empty. That's this case. Otherwise, it has some solution, u1. And then the set of solutions to the linear system is the set of u2 such that u2 minus u1 belongs to the set of solutions to the homogeneous linear system. And we use a substitution. We substitute v for u2 minus u1, which means u2 equals u1 plus v. So we can rewrite this set in this way, and that proves what we wanted to prove, that the set of solutions is an affine space. Now, we proved more than the theorem. We proved that if u1 is a solution to a linear system, then the set of all solutions to the linear system have this form, u1 plus v for all v in big V, where big V is the set of solutions to the corresponding homogeneous system. Here are some implications of that. So long ago we asked, how can we tell if a linear system has only one solution? Well, this gives us a hint. If a linear system has a solution, u1, then that solution is unique if and only if the set of solutions to the homogeneous linear system consists of just one solution. And we know that the homogeneous linear system always contains the 0 vector as a solution. So that must be the only solution to the homogeneous linear system for u1 to be the unique solution to the original linear system. We also asked, how can we find the number of solutions to a linear system over G of 2? Well, now we know the number of solutions could be 0, could be the solution set is the empty set. Otherwise, the number of solutions is equal to the number of solutions to the corresponding homogeneous linear system.